In 1965, astronaut Ed White floated outside his spacecraft, tethered by a single cord, becoming America's first spacewalker. What NASA didn't tell the public was that his spacesuit nearly killed him. White's core temperature spiked to 102 degrees Fahrenheit, while his heart rate climbed to dangerous levels during the 22-minute spacewalk. The same life support systems that enabled that historic spacewalk are the foundation for every EVA suit worn by astronauts today, including those planned for Mars missions. Project Gemini pioneered the techniques that make modern spacewalking possible, but the price was measured in near-death experiences like White's overheating crisis and Neil Armstrong's spinning disaster on Gemini 8. The procedures that nearly killed these astronauts now guide every spacecraft that approaches the International Space Station, the hidden foundation of modern space travel. Today's SpaceX Dragon capsules dock with the International Space Station using procedures that nearly ended missions in 1966. The automated approach sequences, the docking collar mechanisms, even the backup manual controls trace their origins to 10 Gemini missions that came within seconds of disaster. Yet Gemini remains less familiar than Mercury or Apollo, despite being the program that solved the fundamental problems of space travel through trial and error that pushed human endurance to its absolute limits. Apollo receives the glory as the program that put men on the moon, but Apollo astronauts used techniques perfected during Gemini's brutal learning curve. Neil Armstrong and Buzz Aldrin performed their lunar rendezvous using calculations developed after Gemini 8 spun out of control. Without Gemini's deadly experiments, Apollo would have been impossible. The gap between Mercury's simple orbital flights and Apollo's complex lunar missions represented a technological chasm that NASA had no idea how to bridge. Mercury astronauts rode their capsules like passengers on a roller coaster with minimal control over their spacecraft's movement. Apollo required astronauts to pilot their vehicles with precision through orbital maneuvers that had never been attempted. The difference between shooting a man into orbit and landing him on the moon was like the difference between throwing a ball and performing surgery. Someone had to figure out how to transform astronauts from passengers into pilots, and that someone was Gemini. The program existed because NASA administrators recognized that Mercury's successes meant nothing in the context of lunar missions. Mercury capsules could not maneuver in orbit, could not dock with other spacecraft, and could not support spacewalks longer than a few minutes. Apollo spacecraft needed to perform complex rendezvous maneuvers, dock with the lunar module, and support spacewalks lasting hours. The technological gap was so wide that engineers questioned whether it could be bridged at all. Gemini would either solve these problems or prove them unsolvable, and the stakes were America's entire space program. Today's SpaceX missions rely on autonomous docking systems that trace their software lineage directly to Gemini's manual procedures. The radar tracking systems that guide Dragon capsules to the ISS evolved from the handheld radar units that Gemini astronauts use to locate their target vehicles. The thruster control systems that maintain spacecraft orientation during docking maneuvers operate on principles first tested during Gemini flights. Even the abort procedures that protect modern astronauts were written in response to Gemini emergencies that nearly killed their crews. Every International Space Station docking operation uses procedures developed during Gemini missions where astronauts came within seconds of death. The approach vectors that bring spacecraft together safely were calculated after Gemini crews overshot their targets and ran out of fuel. The docking collar designs that connect spacecraft without damaging them were perfected after Gemini 8's collar malfunction sent Armstrong and Scott tumbling toward Earth. The emergency separation procedures that protect astronauts when docking goes wrong were written after that same mission nearly ended in disaster. The cost of Gemini's trial and error approach was measured in astronaut lives that hung in the balance during every mission. Gemini 4's Ed White nearly died from heat exhaustion during a spacewalk when his cooling system failed. Gemini 5's crew drifted powerless in orbit when their fuel cells malfunctioned. Gemini 8's Neil Armstrong and David Scott came within minutes of unconsciousness as their spacecrafts spun out of control. Gemini 9's Eugene Cernan abandoned his spacewalk when his suit overheated and his visor fogged over. Each near-death experience taught NASA something crucial about the realities of space travel. These failures nearly destroyed the entire moon program by revealing problems that nobody had anticipated. The spacewalk difficulties suggested that astronauts might not be able to work outside their spacecraft on the lunar surface. The fuel cell failures indicated that long-duration missions might be impossible. The docking problems suggested that lunar rendezvous might be too dangerous to attempt. Each Gemini crisis forced NASA to confront the possibility that Kennedy's moon landing goal was unattainable. NASA's current Artemis program depends on life support systems that evolved from Gemini's failures. The spacesuits that will protect astronauts during lunar surface operations use cooling systems developed after Ed White's near-fatal spacewalk. The environmental control systems that maintain cabin pressure use backup procedures written after Gemini missions lost pressurization. The navigation systems that will guide astronauts to the lunar surface operate on principles first tested during Gemini's orbital rendezvous attempts. Mars mission planners study Gemini's long-duration flights to understand how astronauts cope with extended isolation and equipment failures. The psychological profiles that determine crew compatibility trace their methods to Gemini's two-man crews who spent 2 weeks trapped together in a space smaller than a phone booth. The emergency procedures that will protect Mars-bound astronauts evolved from the life-threatening situations that Gemini crews faced and survived. The redundant systems that ensure mission success were designed to prevent the single-point failures that nearly killed Gemini astronauts. Understanding Gemini reveals why modern space travel works with such apparent ease. The automated systems that make SpaceX launches look routine incorporate lessons learned from Gemini's manual procedures. The safety margins that protect astronauts today were calculated from Gemini's near disasters. The training programs that prepare astronauts for space missions evolved from Gemini's trial and error approach to spacewalk preparation. A successful space mission since 1966 has benefited from the knowledge purchased with Gemini astronauts' lives. The specific moments when Gemini astronauts faced death created the technologies that enable modern space exploration. Armstrong's split-second decision to abort Gemini 8's docking saved his life and led to the abort systems that protect astronauts today. White struggled to re-enter his spacecraft after his spacewalk led to the airlock designs used on the International Space Station. CERN's overheated spacewalk led to the cooling systems that will protect astronauts on Mars. Each life-threatening moment generated knowledge that makes space travel safer today. Project Gemini transformed space travel from a series of dangerous stunts into a reliable method of transportation. Before Gemini, astronauts were passengers who hoped their spacecraft would function properly. After Gemini, astronauts became pilots who could control their spacecraft and survive equipment failures. The difference between Mercury's simple orbital flights and Apollo's complex lunar missions was bridged by Gemini's willingness to risk astronaut lives to solve the fundamental problems of space travel. The program's legacy lives in every spacecraft that docks with the International Space Station, every astronaut who walks in space, and every mission that ventures beyond Earth's orbit. But Gemini's greatest achievement was not the techniques it pioneered or the lives it saved. It was proving that NASA could solve impossible problems by accepting impossible risks. The program's $1.3 billion cost in 1967 dollars, equivalent to roughly $9 billion today, purchased something invaluable: the knowledge that human beings could survive in space long enough to reach the moon. That knowledge came at a price that NASA administrators knew they were paying from the beginning. The Titan missile gamble that could have killed everyone. The decision to use military hardware for human spaceflight forced NASA into a gamble that terrified their own engineers. They would strap astronauts to the top of a Titan II intercontinental ballistic missile, a weapon designed to deliver nuclear warheads to enemy cities. The missile had never been intended to carry human cargo, and its fuel system used chemicals so toxic they required ground crews to wear full protective suits during handling operations. The Air Force had built the Titan II as a weapon of mass destruction, not a passenger vehicle, yet NASA had no choice but to use it for their most dangerous missions. The Titan II burned hypergolic propellants that ignited spontaneously when mixed together. The oxidizer, nitrogen tetroxide, was a reddish-brown liquid that produced toxic vapors capable of causing severe respiratory damage. The fuel, a mixture called Aerozine 50, contained hydrazine compounds that caused cancer and liver damage. These chemicals were so dangerous that ground crews wore full protective suits and breathing apparatus during fueling operations. The slightest leak could create a toxic cloud that would force immediate evacuation of the launch area. Launch failures during the Titan II development program revealed the weapon's potential for catastrophic destruction. Test missiles exploded on the pad, creating fireballs that melted steel structures and scattered debris across miles of desert. Others broke apart during ascent, raining burning fuel across the landscape. The Air Force accepted these failures as part of weapon development, but NASA engineers realized they were preparing to place astronauts on top of a device with significant reliability concerns. Early testing revealed problems including pogo oscillation that had to be addressed before the missile could be human-rated. Budget constraints forced NASA to accept the Titan II despite its obvious dangers. The space agency needed a rocket capable of lifting the Tomb and Gemini spacecraft into orbit, but they lacked the funding to develop a new launcher from scratch. The Titan II already existed and was being mass-produced for the Air Force's missile program. Adapting the weapon for human spaceflight would cost a fraction of designing a new rocket, but it would also require astronauts to ride a machine designed to explode over enemy territory. NASA administrators convinced themselves that the missile's reliability would improve with modifications, but they knew they were gambling with human lives. The toxic fuel system created hazards that extended far beyond a launch pad. Hypergolic propellants leaked constantly from the missile's fuel lines and valves, creating a chemical environment that corroded everything it touched. The fuel vapors were toxic enough to cause immediate health problems if inhaled in sufficient concentration. The oxidizer was equally dangerous, capable of causing severe burns and lung damage. Ground crews had to wear protective equipment at all times, and even minor leaks required immediate evacuation of the launch area. The combination of these chemicals created an atmosphere so hostile that it seemed designed to kill rather than sustain human life. Modern Falcon 9 rockets achieve reliability rates exceeding 99%, making them safer than commercial airlines. The Titan II's initial performance during weapons testing required significant improvement before it could be considered safe for human flight. NASA's modifications addressed the missile's most dangerous characteristics, but the fundamental design remained unchanged. The rockets still used toxic hypergolic fuel, still relied on systems designed for weapons rather than crew safety, and still carried the inherent dangers of a device built to destroy rather than transport. The contrast between 1960s missile technology and modern rocket reliability demonstrates how far launch vehicle safety has progressed. NASA's solution to the Titan II's dangers was an ejection seat system that would theoretically save astronauts from exploding rockets. The seats were designed to fire the crew clear of the missile during the first 2 minutes of flight, when the risk of explosion was highest. The system used rocket motors to blast the astronauts away from their spacecraft at forces exceeding 20 times Earth's gravity. The seats would deploy parachutes to carry the crew to safety, assuming they survived the initial ejection forces. The system represented NASA's admission that they expected the Titan II to fail with sufficient frequency to justify an emergency escape system. Test footage of the ejection seat system revealed its own potential for killing astronauts. Dummy figures were strapped into the seats and fired from test rigs to evaluate the system's performance. The footage showed mannequins being torn apart by the ejection forces, their limbs separating from their bodies as the seats accelerated. The parachute deployment sequence frequently failed, sending the test dummies plummeting to Earth. Even when the system worked properly, the G-forces were so extreme that they would likely cause serious injury to human occupants. The ejection seats offered a chance of survival, but they were almost as dangerous as the rockets they were designed to escape. The irony of the Titan II's legacy is that its guidance system innovations became the foundation for modern autonomous docking technology. The missile's inertial guidance unit represented cutting-edge technology for its time, using gyroscopes and accelerometers to maintain precise trajectory control. These same principles guide today's spacecraft during approach and docking operations. The Titan II's guidance system could maintain heading accuracy within fractions of a degree, a capability that modern spacecraft inherit through direct technological lineage. The weapon's precision guidance systems, originally designed to deliver nuclear warheads to specific targets, evolved into the navigation systems that guide cargo capsules to the International Space Station. The transformation of the Titan II from weapon to launch vehicle demonstrates how military technology adapts to civilian purposes. The same rocket that carried Gemini astronauts through toxic fuel exposure and explosive potential became the foundation for reliable space transportation systems. Modern rockets inherit the Titan II's guidance precision, structural engineering, and propulsion concepts while eliminating the dangerous hypergolic fuels and weapons-grade components. The missile's legacy lives in every spacecraft that uses inertial guidance, every rocket that employs twin-engine configurations, and every launch vehicle that prioritizes structural efficiency over raw power. But the Titan II was just the beginning of Gemini's dangers. Once astronauts reached orbit safely, they faced an even deadlier challenge that would push human survival to its absolute limits. When spacewalking nearly became a death sentence, Ed White floated 20 feet above Earth on June 3, 1965, tethered to his Gemini 4 spacecraft by a single gold-plated cord. The first American to walk in space moved through the vacuum with apparent ease, using a handheld maneuvering unit to propel himself around his spacecraft. White's voice crackled over the radio with excitement as he described the view of Earth below and the sensation of floating free in space. Mission Control recorded his vital signs as normal, his oxygen consumption as expected, and his movements as controlled. What the public heard was triumph. What NASA's flight surgeon saw was a man whose overheating nearly exceeded his suit's cooling capacity. The space agency had classified the medical data that revealed how close White came to thermal crisis during his 22-minute spacewalk. His core body temperature spiked to 102 degrees Fahrenheit within minutes of leaving his spacecraft. His heart rate exceeded 180 beats per minute, approaching dangerous levels. His oxygen consumption doubled as his body fought to cool itself in the vacuum of space. The cooling system in his spacesuit, designed to handle normal metabolic heat production, was overwhelmed by the thermal load generated by his overheating body. NASA's flight surgeons watched their monitors in growing alarm, as White's vital signs indicated severe heat stress. The Gemini spacesuit's cooling system relied on a simple ventilation fan to circulate oxygen through the suit's fabric layers. The system was adequate for the controlled environment inside the spacecraft, where temperatures remained stable and physical exertion was minimal. In the vacuum of space, where the sun's radiation heated the suit's outer surface to over 200 degrees Fahrenheit, the air-cooled ventilation system proved catastrophically inadequate. The suit's insulation trapped White's body heat while the cooling system failed to remove the thermal buildup. Within minutes of beginning his spacewalk, White was trapped inside what had become a potentially dangerous oven. Mission Control's flight director watched White's telemetry data with growing concern as the astronaut's condition deteriorated. The medical monitors showed classic signs of heat exhaustion, elevated heart rate, increased breathing, and rising core temperature. The flight surgeons recommended immediate termination of the spacewalk, but White's enthusiastic radio transmission suggested he was unaware of his dangerous condition. The euphoria in his voice masked the fact that his body was struggling to cope with the thermal stress of working in space. The disconnect between White's apparent well-being and his actual medical condition created a crisis that pushed the limits of his suit's life support systems. The situation became critical when White attempted to return to his spacecraft and discovered that the hatch mechanism had malfunctioned. The outer hatch cover refused to close properly, preventing him from re-entering the pressurized cabin. White found himself trapped outside his spacecraft with his oxygen supply depleting and his body temperature continuing to rise. The hatch's sealing mechanism had been compromised by suit ballooning, where the pressurized suit expanded in the vacuum and made the astronaut's movements clumsy and difficult. White and his crewmate James McDivitt worked frantically to force the hatch closed while Mission Control calculated how much time remained before White's life support system failed completely. The hatch finally sealed after 12 agonizing minutes of struggle, but not before White's oxygen reserves dropped to dangerously low levels. His suit's primary life support system registered pressure readings that indicated less than 10 minutes of breathing gas remained. The backup oxygen supply had been consumed during the extended spacewalk, leaving no safety margin for the hatch closure delays. When White finally collapsed into his seat, his body temperature had reached 103 degrees and his heart rate remained elevated for hours after the spacewalk ended. The medical team's post-flight examination revealed that White had pushed his suit's thermal management system to its absolute limits. Modern extravehicular activity suits used on Mars missions incorporate redundant cooling systems that prevent the thermal failures that overwhelmed White's air-cooled system. Current spacesuits employ water-cooled garments that circulate chilled liquid through tubes embedded in the suit's inner layer. The water cooling system can remove heat loads exceeding 2,000 watts, compared to the Gemini suit's 200-watt capacity. Modern suits also feature backup cooling systems that activate automatically if the primary system fails. The thermal control systems in contemporary spacesuits can maintain safe body temperatures for 8 hours of continuous heavy work in space, compared to the Gemini suit's 20-minute limitation. White's thermal crisis led directly to the development of water-cooled spacesuits that protect astronauts today. NASA engineers recognized that air cooling was insufficient for extended spacewalks and began developing liquid cooling systems immediately after the Gemini 4 mission. The water-cooled garments first used during Apollo missions traced their design directly to the thermal management problems that overwhelmed White's air-cooled system. The liquid cooling concept proved so effective that it became standard for all subsequent spacesuits, including those used on the International Space Station and those being developed for Mars exploration. Current International Space Station maintenance procedures incorporate safety protocols written in response to Gemini's spacewalk thermal crises. Modern EVA operations require continuous monitoring of astronaut vital signs, with automatic termination protocols if thermal stress indicators exceed safe limits. The buddy system used during ISS spacewalks ensures that no astronaut works alone outside the station, preventing the isolation that pushed White's cooling system to its limits. Current procedures mandate backup life support systems with sufficient capacity to sustain astronauts for twice the planned EVA duration, eliminating the oxygen depletion problems that plagued Gemini missions. The classified medical data from Gemini spacewalks revealed that astronauts routinely approached heat stroke during relatively brief excursions outside their spacecraft. Eugene Cernan's Gemini 9 spacewalk ended prematurely when his visor fogged over from excessive perspiration caused by thermal stress. Richard Gordon's Gemini 11 EVA was terminated after his heart rate exceeded 200 beats per minute and his core temperature reached dangerous levels. Buzz Aldrin's successful Gemini 12 spacewalk succeeded only because NASA had finally developed adequate cooling systems based on the failures that overwhelmed his predecessors. The thermal management systems that keep astronauts alive during spacewalks today evolved directly from the life support failures that characterized Gemini's EVA program. The water-cooled garments that regulate body temperature during 8-hour spacewalks trace their development to White's overheating emergency. The redundant cooling systems that provide backup thermal protection evolved from the single-point failures that pushed Gemini astronauts to their thermal limits. The automated monitoring systems that track astronaut vital signs during EVAs were developed after flight surgeons watched helplessly as White's condition deteriorated in real time. Every spacewalk conducted since 1965 has benefited from the thermal management technologies developed to prevent the life support failures that overwhelmed Gemini astronauts. The cooling systems in modern spacesuits, the safety protocols that govern EVA operations, and the medical monitoring systems that track astronaut health all evolved from the thermal crises experienced by White and his fellow Gemini spacewalkers. The euphoria of America's first spacewalk masked a cooling system failure that pushed the suit's capabilities to their absolute limits, but that crisis generated the life support technologies that enable today's routine spacewalk operations. But solving the thermal problems of spacewalking was only the beginning of Gemini's challenges. The program faced an even more fundamental obstacle that threatened to make orbital operations impossible. The mathematics of orbital rendezvous defied every instinct that pilots had developed during decades of atmospheric flight. When NASA engineers first calculated the physics of orbital intercepts, they discovered something that seemed to violate common sense. If a spacecraft was trailing behind its target, the pilot's natural instinct would be to speed up to catch up. But firing forward thrusters raises orbit and slows approach, requiring an initial backward thrust to drop into a lower, faster orbit. The faster you tried to go, the slower you actually went. This counterintuitive behavior made orbital rendezvous appear impossible to achieve through conventional piloting techniques. Early rendezvous attempts proved the physics were as unforgiving as the calculations suggested. Gemini 4 astronauts Jim McDivitt and Ed White fired their thrusters toward their target vehicle, expecting to close the distance between the spacecraft. Instead, their capsule rose into a higher orbit and began falling behind their target at an accelerating rate. The crew eventually abandoned the rendezvous attempt when their fuel reserves dropped to dangerously low levels, consuming precious propellant while learning the hard lessons of orbital mechanics. Mission Control watched helplessly as the spacecraft demonstrated exactly why intuitive piloting techniques failed in the vacuum of space. The mathematical explanation behind this phenomenon lay in the fundamental mechanics of orbital motion. Objects in higher orbits move slower than objects in lower orbits, following Kepler's laws of planetary motion. When a spacecraft fires its engines in the forward direction, it adds energy to its orbit and rises to a higher altitude. The higher altitude means slower orbital velocity, causing the spacecraft to fall behind its target rather than catch up. To close distance with a target ahead, A spacecraft must actually slow down to drop into a lower, faster orbit, then speed up at the correct moment to intercept the target. The mathematical breakthrough that solved the rendezvous equations came from a small group of engineers who recognized that orbital mechanics required thinking in 3 dimensions rather than 2. They developed a series of complex calculations that predicted exactly when and where to fire thrusters to achieve intercept trajectories. These equations accounted for the elliptical nature of orbits, the gravitational effects of Earth's mass distribution, and the precise timing required to bring 2 spacecraft together at the same point in space. The mathematics were so complex that they required hours of calculation using the most powerful computers available. Computer limitations in the 1960s forced astronauts to perform many of these calculations by hand using slide rules and paper tables. The onboard computers carried by Gemini spacecraft had less processing power than modern electronic calculators. These primitive machines could store only a few hundred numbers and performed calculations so slowly that complex rendezvous problems required several minutes to solve. When the computers failed completely, as they frequently did, astronauts had to fall back on manual navigation techniques, using star sightings and stopwatches to determine their position and velocity. The rendezvous computer carried aboard Gemini spacecraft weighed 40 pounds and consumed enormous amounts of electrical power. Its memory capacity was so limited that it could store only the most basic navigation programs. The computer's arithmetic unit could perform addition and subtraction but required multiple steps to complete multiplication or division operations. Complex trigonometric calculations needed for rendezvous planning took so long that astronauts often resorted to pre-calculated tables rather than waiting for the computer to finish its work. The machine's reliability was so poor that mission planners always included backup procedures for manual navigation. Modern autonomous docking systems process orbital mechanics calculations thousands of times faster than 1960s computers while carrying vastly more sophisticated software. Today's spacecraft computers can model orbital trajectories in real time, adjusting approach patterns continuously as conditions change. The Dragon capsule's guidance system processes sensor data from multiple sources simultaneously, calculating optimal intercept courses while accounting for atmospheric drag, gravitational variations, and target motion. These systems can plan and execute rendezvous operations with minimal human intervention, accomplishing in minutes what took Gemini astronauts hours to calculate manually. Buzz Aldrin's doctoral dissertation at MIT provided the theoretical foundation that saved the Apollo program from rendezvous failures. His research on orbital rendezvous guided Apollo mission planning by establishing the mathematical techniques needed for precise orbital intercepts under real-world conditions. Aldrin developed simplified calculation methods that astronauts could use without extensive computer support. His work established the standard procedures for approach trajectories, final closure techniques, and emergency abort scenarios. The rendezvous methods he developed became the foundation for all subsequent NASA docking operations, including those used during Apollo lunar missions. Current Mars sample return mission planning relies heavily on rendezvous techniques developed during Gemini flights. The orbital mechanics calculations used to bring sample containers together with return spacecraft follow the same mathematical principles that Aldrin developed for lunar rendezvous. Mission planners use updated versions of Gemini's approach procedures to design intercept trajectories around Mars. The backup navigation methods that will protect Mars missions from computer failures evolved directly from the manual techniques that Gemini astronauts used when their primitive computers failed. The backup procedures that astronauts still use when computers fail during ISS operations were written during Gemini missions. These manual techniques allow crew members to calculate approach trajectories using only basic instruments and pre-computed tables. The procedures account for the limitations of human calculation under stress, providing simplified methods that produce acceptable results without complex mathematics. Modern astronauts train extensively in these backup techniques, ensuring they can complete rendezvous operations even when their sophisticated computer systems fail completely. The rendezvous methods developed through Gemini's dangerous trial and error flights became the foundation for every spacecraft docking operation since 1966. The mathematical techniques that seemed impossible to master during early Gemini missions now operate automatically aboard every vessel that approaches the International Space Station. The manual backup procedures that saved Gemini crews from computer failures still protect astronauts when modern systems fail. But mastering the approach was only half the challenge. The actual moment of contact between spacecraft would prove even more dangerous than the rendezvous itself. The docking mechanism that almost killed Neil Armstrong. Neil Armstrong pushed the docking probe into the Agena target vehicle's collar at 10:14 p.m. on March 16, 1966, achieving the first successful docking between two spacecraft in orbit. The mechanical latches engaged with a solid thunk that both astronauts felt through their seats. Mission Control erupted in celebration as telemetry confirmed that Gemini 8 had locked onto its target. Armstrong reported that the docking felt smooth and stable, with no unusual vibrations or movements. The achievement represented a crucial milestone for the Apollo program, proving that spacecraft could link together in the vacuum of space. 27 minutes later, both astronauts were fighting for their lives as their combined spacecraft spun toward Earth in an uncontrollable tumble. The crisis began with a barely perceptible roll that Armstrong initially attributed to the Agena's control system. The target vehicle had been programmed to maintain attitude control after docking, but something was causing the combined spacecraft to rotate slowly around its longitudinal axis. Armstrong attempted to correct the motion using the Agena's thrusters, but the rotation continued to increase. Within minutes, the gentle roll had accelerated into a violent spin that threatened to tear the spacecraft apart. The centrifugal forces generated by the rotation pressed both astronauts against their seats with increasing intensity. Thruster number 8 in Gemini's attitude control system had become mechanically jammed in the open position, feeding fuel continuously into its combustion chamber. The stuck thruster created an uncontrolled torque that overwhelmed the Agena's stabilization system. The malfunction generated a constant sideways force that spun the docked vehicles like a baton thrown by a twirler. The thruster continued firing even when Armstrong commanded it to stop, consuming precious fuel while accelerating the deadly spin. Armstrong's training had prepared him for thruster failures, but not for a malfunction that occurred while docked to another spacecraft. The standard procedure called for isolating the failed thruster and using the remaining attitude control system to stabilize the spacecraft. However, the Agena's mass and inertia made the combined vehicle nearly impossible to control using Gemini's remaining thrusters. The docked configuration created a mechanical nightmare where the malfunctioning thruster's torque was amplified by the Agena's weight distribution. Armstrong found himself piloting a machine that was designed to be stable but had become lethally unstable. The spacecraft's rotation rate reached 1 revolution per second, creating G-forces that threatened to cause both astronauts to lose consciousness. Armstrong's vision began to blur as the centrifugal force pressed him against his seat with nearly 4 times his normal weight. David Scott reported that he was having difficulty reading his instruments as the spinning motion made focusing impossible. The physiological effects of the rotation were approaching the threshold where human beings lose the ability to function. Mission Control calculated that the astronauts had perhaps 2 minutes before the G-forces would render them unconscious. Armstrong made the split-second decision to separate from the Agena target vehicle, despite knowing that undocking would end their mission prematurely. The separation procedure required precise timing and coordination between both astronauts while they were being subjected to extreme rotational forces. Armstrong fired the undocking mechanism just as the spacecraft completed one of its rotations, hoping to break free cleanly without damaging either vehicle. The undocking succeeded, but the Gemini spacecraft continued spinning at the same dangerous rate because the stuck thruster was still firing. The undocking revealed that the malfunction was aboard the Gemini spacecraft rather than the Agena target vehicle. Armstrong watched through his window as the Agena stabilized itself after separation, confirming that his spacecraft was the source of the problem. The realization meant that he had to shut down the entire attitude control system and switch to the re-entry control system to regain stability. Using the re-entry thrusters meant that the mission would have to be terminated immediately, as those thrusters were reserved for the final phases of flight. Armstrong activated the re-entry control system and began the delicate process of stopping the spacecraft's rotation using thrusters that were designed for atmospheric re-entry rather than orbital maneuvering. The re-entry thrusters were more powerful than the attitude control system, but they were also less precise and consumed fuel at a much higher rate. Armstrong had to fire short bursts in the opposite direction of the spin while avoiding overcorrection that would send the spacecraft tumbling in the other direction. The procedure required perfect timing and steady hands while experiencing disorienting rotational forces. The spacecraft's spin gradually decreased as Armstrong worked the re-entry control system, but the fuel consumption meant that Gemini 8 would have to return to Earth within hours rather than completing its planned 3-day mission. The re-entry fuel was reserved for the final descent through Earth's atmosphere, and using it for attitude control left no margin for error during the actual re-entry sequence. Mission Control calculated that the spacecraft had just enough fuel remaining to achieve a controlled re-entry if they began the process immediately. Modern International Space Station docking mechanisms incorporate multiple redundant systems that prevent the single-point failures that nearly killed Armstrong and Scott. Current docking collars include emergency separation systems that can be activated independently by either spacecraft. The mechanisms are designed to fail safely, with spring-loaded separation systems that push the vehicles apart if power is lost. Modern docking systems also include attitude control coordination between spacecraft, preventing the torque amplification that made the Gemini 8 emergency so dangerous. The safety protocols developed after the Gemini 8 incident require extensive pre-docking checks of all attitude control systems and mandate that both spacecraft maintain independent control authority during docking operations. Current procedures include abort triggers that automatically separate spacecraft if rotation rates exceed safe limits. The protocols also require that docking operations be conducted with sufficient fuel reserves to handle emergency situations without compromising mission safety. The lunar module's docking system incorporated multiple design changes that were directly influenced by the Gemini 8 incident. The Apollo docking mechanism included redundant latching systems that prevented the single-point failures that characterized earlier designs. The lunar module's attitude control system was designed with isolation valves that could shut down individual thrusters without affecting the entire system. The docking emergency that nearly killed the first man to walk on the moon created the safety systems that protect astronauts today. But mechanical failures were only one category of crisis that threatened Gemini missions. The spacecraft's electrical systems would prove equally capable of turning routine flights into survival emergencies. The fuel cell crisis that revolutionized space power. Gordon Cooper and Pete Conrad found themselves managing a power crisis 36 hours into their Gemini 5 mission when oxygen pressure readings in the fuel cells dropped below safe operating levels. The spacecraft's electrical systems shut down automatically as a safety measure, cutting communication links with Earth and stopping telemetry data flow to mission control. The astronauts activated emergency battery power to maintain life support, but the batteries carried only enough charge for a few hours of operation. Cooper and Conrad faced the possibility of spending 6 more days in orbit with severely limited electrical power, no maneuvering capability, and intermittent communication with Earth. The oxygen pressure readings made no sense to the engineers monitoring the mission from Houston. The fuel cells were designed to operate at specific pressure levels, and the sudden drop indicated a catastrophic failure somewhere in the system. The readings showed pressures far below the minimum required for fuel cell operation, yet the cells had been functioning normally just hours earlier. Flight controllers scrambled to understand what could cause such a rapid pressure loss while the spacecraft continued orbiting Earth with limited radio contact. The pressure readings suggested that the fuel cells might become unstable if they continued operating, forcing mission control to recommend immediate shutdown of all electrical systems. A faulty heater inside the oxygen tank had triggered the crisis that threatened to end the mission on its first day. The heater was designed to maintain proper pressure levels by warming the oxygen supply, but the device had failed completely. Without the heater's warmth, the oxygen inside the tank began to cool and contract, reducing the pressure below the minimum required for fuel cell operation. The malfunction seemed insignificant compared to the complex systems aboard the spacecraft, yet it had rendered the primary electrical system inoperable. The failure demonstrated how a single component could cascade into mission-threatening problems. Cooper immediately began implementing power conservation measures to keep the crew alive until engineers could solve the pressure problem. He shut down all non-essential electrical systems, including the navigation computer, attitude control thrusters, and communications equipment. The spacecraft's interior lights went dark, leaving the astronauts to work by the faint glow of essential instrument panels. Cooper switched off the cabin heating system, knowing that the temperature would drop to uncomfortable levels within hours. The power conservation measures bought time, but they also left the spacecraft unable to maneuver or maintain continuous communication with Earth. The fuel line heaters shut down automatically when Cooper cut power to non-essential systems, setting off another cascade of failures that threatened the mission. The heaters were designed to keep the spacecraft's propellant lines warm enough to prevent freezing in the vacuum of space. Without the heaters, the fuel lines began to cool rapidly as the spacecraft passed through Earth's shadow during each orbit. The propellant inside the lines started to freeze, creating ice blockages that prevented the thrusters from firing. The frozen fuel lines left the astronauts with no ability to maneuver their spacecraft or adjust their orbit. The fuel cell technology that NASA had chosen for Gemini 5 represented a significant advancement over the battery systems used in earlier missions. The fuel cells combined hydrogen and oxygen to produce electricity, offering much greater power output for their weight compared to conventional batteries. The system was designed to operate continuously for 8 days, providing the electrical power needed for extended missions. The fuel cells also produced water as a byproduct, which the astronauts could drink during their flight. However, the heater failure forced the crew to rely on battery power for the final orbits, demonstrating the vulnerability of this advanced technology to simple component failures. Modern spacecraft power systems incorporate multiple redundant fuel cell stacks that prevent the single-point failures that crippled Gemini 5. Contemporary fuel cells include backup heating systems that maintain proper operating temperatures even if primary heaters fail. The systems also feature pressure monitoring devices that can detect problems before they cause complete power loss. Modern fuel cells can operate at lower pressures than their 1960s predecessors, providing operational flexibility that prevents the cascading failures that nearly ended Cooper and Conrad's mission. The crisis led directly to the development of redundant power systems that protect Mars rovers during their extended missions on the planet's surface. The rovers use radioisotope thermoelectric generators that provide continuous power without the pressure-sensitive fuel cell technology that failed during Gemini 5. The RTG systems include multiple redundant heating elements that prevent the thermal failures that disabled the Gemini spacecraft. The power systems also incorporate backup batteries that can maintain operations during equipment failures or dust storms that reduce solar panel efficiency. Current International Space Station energy management systems use multiple power sources and automated switching systems that prevent the total power loss that occurred during Gemini 5. The ISS relies on large solar arrays for primary power, with backup batteries that automatically engage when the station passes through Earth's shadow. The power distribution system includes multiple redundant pathways that route electricity around failed components. The station's fuel cells provide backup power for critical systems, but they operate independently from the main power grid to prevent cascading failures. The backup procedures developed after Gemini 5's power crisis prevented similar failures during Apollo missions by incorporating multiple independent power sources. Apollo spacecraft carried 3 separate fuel cell systems, each capable of providing sufficient power for the entire mission. The fuel cells included redundant heating systems and pressure monitoring devices that could detect problems before they caused power loss. The spacecraft also carried backup batteries that could maintain life support systems during fuel cell maintenance or failures. The fuel cell technology that nearly ended the Gemini 5 mission became the foundation for every long-duration space mission since 1965. The pressure monitoring systems that detected the oxygen problem during Gemini 5 evolved into the sophisticated diagnostic systems that protect modern spacecraft. The power conservation techniques that Cooper and Conrad used to survive their electrical crisis became standard procedures for emergency power management. The redundant heating systems that prevent fuel cell failures today trace their development directly to the heater malfunction that nearly ended the Gemini 5 mission. But power failures were not the only threat that Gemini crews faced. The Agena target vehicle's explosive secret. The Agena target vehicle that Gemini astronauts were supposed to dock with suffered 2 spectacular launch failures that nearly ended the Rendezvous program. The vehicle designated GATV 5004 for Gemini 6 detonated during launch on October 25, 1965, creating a fireball that could be seen from miles away. The explosion scattered debris across the Atlantic Ocean and left astronauts Wally Schirra and Tom Stafford without a target for their rendezvous mission. 3 months later, the Agena intended for Gemini 9 suffered engine failure during ascent, forcing NASA to deploy the backup augmented target docking adapter. These failures revealed fundamental problems with adapting military hardware for civilian space operations. The Agena's explosive tendencies stemmed from its origins as a reconnaissance satellite designed for military intelligence operations. Lockheed had originally developed the vehicle to carry spy cameras over enemy territory, where reliability mattered less than performance and secrecy. The Agena's engine was designed for single-use missions that ended when the satellite completed its intelligence gathering mission. Military planners accepted higher failure rates as the cost of obtaining critical intelligence, but NASA needed the vehicle to survive long enough for astronauts to practice docking procedures. The agency found itself dependent on hardware that was designed to be expendable rather than reliable. The Agena's engine suffered from a phenomenon known as hard start, where the combustion chamber would ignite with explosive force rather than the smooth burn required for normal operation. The hard start occurred when hypergolic fuel and oxidizer mixed in the wrong proportions or at the wrong time during the ignition sequence. The resulting explosion would destroy the engine and often the entire vehicle within seconds of startup. The hard start problem was particularly dangerous during orbital operations, where the engine needed to restart multiple times to maintain proper attitude in orbit. The unpredictable nature of hard starts meant that astronauts never knew whether their target vehicle would explode when they commanded it to fire its engines. Lockheed's rushed modifications to adapt the spy satellite for civilian use created additional failure modes that compounded the vehicle's existing problems. The company had added docking hardware and attitude control systems without fully understanding how these modifications would interact with the existing propulsion system. The additional mass and different center of gravity changed the vehicle's dynamic characteristics in ways that affected engine performance. The modifications also required additional electrical systems that drew power from the vehicle's batteries, reducing the electrical margins needed for reliable engine operation. The hasty nature of these modifications meant that testing was limited and many problems only became apparent during actual missions. The hard start phenomenon that plagued Agena engines occurred when the fuel injection system delivered propellants to the combustion chamber at uneven rates. The engine was designed to ignite smoothly when fuel and oxidizer mixed in precise ratios, but manufacturing tolerances and component wear could cause the mixture to become unstable. When the mixture ratio was wrong, the initial combustion would create pressure waves that disrupted the fuel flow and caused the engine to explode rather than burn steadily. The explosion would rupture the combustion chamber and often trigger secondary explosions in the fuel tanks. The hard start problem was inherent to the engine design and could not be eliminated without complete redesign of the propulsion system. Modern spacecraft docking systems achieve reliability rates exceeding 99.5% through redundant design and extensive testing that were impossible during the Agena era. Contemporary target vehicles use multiple independent propulsion systems that prevent single-point failures from destroying the entire spacecraft. The engines incorporate staged ignition systems that prevent hard starts by gradually building up combustion pressure rather than attempting immediate full power operation. Modern systems also include health monitoring sensors that can detect abnormal conditions before they cause catastrophic failures. The reliability improvements mean that modern spacecraft can perform dozens of engine starts without the explosive failures that characterized Agena operations. The Agena failures forced NASA to develop the Augmented Target Docking Adapter as a backup system that could provide docking practice without the explosive risks of the original vehicle. The ADDA was designed specifically for the Gemini program rather than being adapted from military hardware. The adapter included a simplified docking collar and basic attitude control systems, but eliminated the complex propulsion system that caused most Agena failures. The ATDA's reliability proved much higher than the Agena's, demonstrating that purpose-built hardware performed better than adapted military systems. The backup system provided the docking practice that astronauts needed while avoiding the explosive failures that had destroyed multiple Agena vehicles. Current space missions incorporate multiple backup systems that prevent the single-point failures that made Agena operations so dangerous. Modern spacecraft include redundant propulsion systems that can maintain attitude control even if primary engines fail. The vehicles also carry backup electrical systems that ensure critical functions continue operating during component failures. Contemporary mission planning includes abort procedures that allow astronauts to complete their objectives using alternative target vehicles if primary systems fail. These backup systems evolved directly from the lessons learned during Agena's explosive failures. The explosive failures of Gemini's target vehicles established the reliability standards that make modern space docking operations routine rather than dangerous experiments. The failure analysis that followed each Agena explosion created testing procedures that prevent similar problems in contemporary systems. The backup procedures that protected astronauts from Agena failures became standard elements of modern mission planning. The reliability standards that emerged from Agena's explosive legacy ensure that today's spacecraft can dock safely without the constant threat of catastrophic failure that characterized the Gemini program. But even when the target vehicles worked properly, astronauts discovered they could barely function outside their spacecraft. The underwater training revolution that saved spacewalking. Eugene Cernan floated outside his Gemini 9 spacecraft on June 5, 1966, attempting to strap himself into an experimental maneuvering unit that would allow him to fly independently through space. The device was mounted on the rear of the spacecraft, requiring Cernan to work his way around the vehicle's exterior using handholds and tethers. Within minutes of beginning the task, Cernan's heart rate spiked above 180 beats per minute, and his visor began fogging over from excessive perspiration. The simple act of moving around the spacecraft's exterior had exhausted him to the point where he could barely see his instruments. Mission Control watched helplessly as Cernan struggled with tasks that should have taken minutes, not hours. The pattern of spacewalk failures had become disturbingly consistent across multiple Gemini missions. Each mission revealed that astronauts could barely function outside their spacecraft, much less perform the complex tasks required for lunar missions. NASA engineers struggled to understand why trained astronauts could not complete simple mechanical tasks in the weightless environment of space. The astronauts were physically fit and had practiced their procedures extensively using ground-based simulators. The tasks themselves were straightforward operations like connecting cables, operating switches, and moving equipment from one location to another. Yet in space, these same tasks became nearly impossible due to the unexpected physical demands of working in a weightless environment. The engineers began to suspect that their ground-based training methods were inadequate for preparing astronauts for the realities of spacewalk operations. Traditional training methods used air-bearing tables and suspension systems that could only approximate weightlessness in limited ways. These systems could not simulate the complex three-dimensional movements required for spacewalk operations. The breakthrough came when someone at NASA suggested using swimming pools to simulate the weightless conditions that astronauts experience during spacewalks. The concept seemed almost absurd at first, since water provided resistance while space provided none. However, underwater training offered the closest approximation to weightlessness that could be achieved on Earth. Neutral buoyancy experiments had begun informally in 1962 when NASA engineers first explored underwater training possibilities. These early tests involved simple submersion exercises to evaluate whether water could simulate the movement characteristics of weightless environments. The initial results were promising enough to warrant further investigation, but the technique remained experimental until the repeated failures of Gemini spacewalks forced NASA to formalize the approach. The underwater training methods became official NASA procedure after Gemini 9's difficulties demonstrated that conventional preparation techniques were insufficient for EVA operations. Buzz Aldrin emerged as the leading advocate for underwater training after his own experiences with the frustrating limitations of ground-based simulators. Aldrin recognized that underwater training provided a more realistic environment for developing the muscle memory and technique needed for effective EVA operations. He began spending hours in swimming pools, practicing the precise movements and positioning that would be required for his upcoming Gemini 12 mission. Objects underwater moved in 3 dimensions and required careful control to prevent unwanted motion. The water's buoyancy supported the astronauts' weight while allowing free movement in all directions. Most importantly, underwater training revealed the physical techniques needed to work effectively in an environment where every action produced an equal and opposite reaction. The underwater training techniques that Aldrin developed revolutionized NASA's approach to spacewalk preparation. Astronauts learned to move deliberately and slowly, using small controlled movements rather than the quick motions that worked on Earth. They practiced anchoring themselves to handholds before attempting to operate equipment, preventing the unwanted rotation that had plagued earlier missions. The training taught astronauts to anticipate the reaction forces generated by their movements and to position themselves accordingly. Most importantly, the underwater sessions revealed the physical endurance required for extended EVA operations, allowing astronauts to build the stamina needed for successful spacewalks. Aldrin's neutral buoyancy rehearsals in 1966 transformed Gemini 12 into the program's first completely successful spacewalk mission. His mission demonstrated that astronauts could perform useful work outside their spacecraft without the life-threatening exhaustion that had characterized earlier missions. Aldrin set an EVA record of 5 hours and 30 minutes for 1 spacewalk and 2 stand-up exercises, proving that underwater training could prepare astronauts for extended operations in space. His success was directly attributable to the underwater training methods that had taught him to move efficiently and position himself properly during EVA operations. The mission proved that spacewalking could be safe and productive when astronauts were properly prepared using realistic training methods. The neutral buoyancy techniques developed during Gemini training became the foundation for all subsequent astronaut preparation. Underwater training pools allowed astronauts to practice complete mission sequences in a realistic environment that simulated the challenges of working in space. The training revealed the importance of proper body positioning, the need for secure anchor points, and the techniques required to perform precise mechanical operations while floating freely. The pools also provided a safe environment for astronauts to learn from mistakes without the life-threatening consequences of errors during actual spacewalks. Modern astronaut preparation methods have evolved from the basic underwater training techniques pioneered during the Gemini program. Today's neutral buoyancy laboratory at Johnson Space Center contains a massive pool measuring 202 feet long, 102 feet wide, and 40 feet deep. The pool holds 6.2 million gallons of water and contains full-scale mock-ups of International Space Station components. Astronauts spend hundreds of hours in this facility, practicing every aspect of their planned spacewalks in an environment that closely simulates the weightless conditions of space. The training protocols developed during Gemini missions provide the foundation for these modern preparation methods. The massive training pools used today trace their origins directly to the simple swimming pool sessions that saved the Gemini program. NASA recognized that underwater training was so effective that they began constructing specialized facilities designed specifically for astronaut preparation. The first dedicated neutral buoyancy facility was built in the 1970s, followed by increasingly sophisticated pools that could accommodate full-scale spacecraft mock-ups. These facilities became essential elements of astronaut training, with every spacewalk being rehearsed extensively underwater before being attempted in space. Current Mars mission preparation relies heavily on underwater training techniques that evolved from Gemini's spacewalk failures. Mars surface operations will require astronauts to perform complex tasks while wearing bulky pressure suits in a reduced gravity environment. The underwater training methods developed during Gemini missions provide the foundation for preparing astronauts to work effectively under these challenging conditions. The techniques for maintaining body position, conserving energy, and performing precise mechanical operations remain essentially unchanged from those pioneered by Buzz Aldrin during his underwater training sessions. The underwater training revolution that began with simple swimming pool sessions transformed spacewalking from a dangerous experiment into a routine operation. Every astronaut who has walked in space since 1966 has benefited from the training methods that emerged from Gemini's failures. The neutral buoyancy techniques that saved the Gemini program continue to prepare astronauts for the most challenging EVA operations, including those planned for future missions to Mars and beyond. The swimming pool sessions that seemed like a desperate attempt to solve an impossible problem became the foundation for humanity's ability to work effectively in the weightless environment of space. But solving the human factors of spacewalking was only part of Gemini's challenge. The spacecraft carried revolutionary technology that promised to automate navigation and guidance, yet this cutting-edge system would prove less reliable than the manual techniques it was designed to replace. The computer that couldn't compute. The Gemini guidance computer represented the pinnacle of 1960s technology when it was installed aboard each spacecraft. The revolutionary device weighed nearly 60 pounds and contained 4,096 words of core memory, each storing a 39-bit word composed of 3 13-bit syllables. Instructions required a 4-bit opcode and 9 bits of operand data, creating a programming environment so primitive that simple navigation calculations required several minutes to complete. The machine represented humanity's first attempt to navigate through space using digital computation, but its limitations forced astronauts to rely on manual backup methods that proved more reliable than the cutting-edge technology. Mission Control watched helplessly as the Gemini 6 computer failed during a critical rendezvous maneuver, leaving astronauts Wally Schirra and Tom Stafford to navigate using star sightings and slide rules while traveling at 17,500 miles per hour. The computer's failure occurred at the moment when precise navigation was most crucial, forcing the crew to revert to manual techniques that required them to identify specific stars and calculate their position using handheld instruments. Schirra pulled out a slide rule and began performing trigonometric calculations while Stafford used a sextant to measure star angles. The backup navigation methods worked, but they required mathematical skills and steady hands that few people possessed in the stressful environment of orbital flight. The computer's arithmetic unit could perform basic addition and subtraction operations, but multiplication and division required multiple processing cycles that consumed precious time during critical mission phases. Complex calculations like orbital mechanics equations took so long that astronauts often abandoned the computer in favor of pre-calculated tables that provided faster answers. The machine's memory capacity was so limited that it could store only essential navigation programs, leaving no room for backup software or error correction routines. When the computer encountered unexpected conditions, it would simply stop functioning rather than attempting to find alternative solutions. Astronauts carried paper tables and charts that contained pre-calculated navigation data for every conceivable mission scenario. These tables included orbital mechanics equations, fuel consumption rates, and timing data for thruster burns. The paper backup systems were developed after early computer failures left crews unable to complete their missions. Frank Borman and James Lovell used these manual techniques extensively during their Gemini 7 flight when their computer malfunctioned repeatedly. The paper tables proved more reliable than the digital systems, providing accurate navigation data even when the spacecraft's electrical systems failed completely. The slide rule became an essential tool for Gemini astronauts who needed to perform complex calculations when their computer failed. The mechanical device could handle trigonometric functions, logarithmic calculations, and basic arithmetic operations without requiring electrical power. Astronauts practiced using slide rules during training until they could perform orbital mechanics calculations accurately under the stress of spaceflight. The slide rule's reliability made it superior to the computer for many navigation tasks, since it could not malfunction or suffer from electrical problems that plagued the digital systems. Star navigation techniques that had guided sailors for centuries became backup procedures for space missions when computer systems failed. Astronauts learned to identify specific stars and measure their angles using handheld sextants to determine their spacecraft's position and velocity. The star sighting procedures required extensive training and practice, since the techniques had to be performed while wearing pressure suits and dealing with the disorienting effects of weightlessness. The manual navigation methods proved so reliable that they became standard backup procedures for all subsequent space missions. Modern spacecraft autonomous systems process navigation data using computers that are millions of times more powerful than the Gemini guidance computer. Contemporary spacecraft computers can perform complex orbital mechanics calculations in real time, while simultaneously managing life support systems, communications, and propulsion controls. The International Space Station's computers process navigation data continuously, making thousands of calculations per second to maintain precise orbital position. These modern systems include multiple redundant processors that can take over automatically if primary systems fail, preventing the navigation crises that plagued Gemini missions. The computer failures that forced Gemini astronauts to navigate manually led directly to the development of redundant navigation systems that protect modern spacecraft. Current space missions include multiple independent navigation computers that cross-check each other's calculations to detect errors before they become dangerous. The backup systems are designed to function even if primary computers fail completely, ensuring that astronauts can always determine their position and navigate safely. The redundancy philosophy evolved from the lessons learned during Gemini missions where single computer failures created life-threatening situations. Contemporary spacecraft include manual control systems that allow astronauts to pilot their vehicles using techniques pioneered during Gemini missions. The joystick controls for attitude adjustment and T-shaped handles for translation movement trace their design directly to the manual systems that Gemini astronauts used when their computers failed. Modern spacecraft also carry printed navigation tables and emergency procedures that crew members can use without computer assistance. The backup systems ensure that human pilots can maintain control of their spacecraft even when sophisticated automated systems fail completely. The Gemini program's navigation failures created the foundation for spacecraft redundancy that protects modern space missions from computer malfunctions. Every spacecraft launched since 1966 has included backup navigation systems that can function independently of primary computers. The manual calculation techniques that saved multiple Gemini missions became standard emergency procedures for all subsequent space operations. The paper tables and slide rule methods that seemed primitive even in the 1960s remain essential backup tools for astronauts who must navigate through space when technology fails. These backup procedures and redundant systems would prove their worth in ways that NASA never anticipated, forming the invisible foundation beneath every successful space mission that followed. Today's SpaceX Dragon capsules execute their automated approach to the International Space Station using software algorithms that trace their mathematical origins to calculations Buzz Aldrin performed by hand during Gemini 12. The radar systems tracking approaching spacecraft evolved from handheld units that Gemini astronauts used to locate their targets in orbit. The thruster control sequences maintaining precise orientation during docking operations follow the same firing patterns that Neil Armstrong used to stabilize his tumbling spacecraft during the Gemini 8 emergency. Every successful commercial space mission depends on techniques developed through trial and error during 10 Gemini flights that came within seconds of disaster. The life support systems protecting astronauts during Mars missions incorporate technologies that evolved directly from failures that overwhelmed Gemini crews. The water-cooled garments regulating body temperature during spacewalks trace their development to Ed White's overheating crisis during his historic EVA, when his core temperature spiked to 102 degrees and his air-cooled suit proved inadequate for space operations. The redundant cooling systems preventing thermal failures evolved from the single-point cooling system that pushed White's suit to its limits. Modern spacesuits employ water-cooled garments that circulate chilled liquid through tubes embedded in the suit's inner layer, capable of removing heat loads exceeding 2,000 watts compared to the Gemini suit's 200-watt capacity. International Space Station docking operations follow procedures written during Gemini missions that pushed human survival to its absolute limits. The approach vectors bringing spacecraft together safely were calculated after Gemini crews overshot their targets and ran out of fuel during failed rendezvous attempts. The docking collar mechanisms connecting spacecraft without damaging them evolved from the collar malfunction that sent Armstrong and Scott tumbling toward Earth at 1 revolution per second. The emergency separation procedures protecting astronauts when docking goes wrong were developed after Gemini 8's near-fatal spin, when thruster number 8 became mechanically jammed and created uncontrolled torque that overwhelmed the spacecraft's stabilization system. The neutral buoyancy training pools preparing astronauts for Mars surface operations evolved from simple swimming pool sessions that saved Gemini's spacewalk program. Modern astronauts spend hundreds of hours underwater practicing tasks they will perform in space, using techniques that Buzz Aldrin developed to overcome the EVA failures that plagued earlier Gemini missions. The underwater training methods teach astronauts to move efficiently in weightless environments, conserve energy during extended operations, and maintain proper body position while performing complex tasks. Aldrin's neutral buoyancy rehearsals in 1966 transformed Gemini 12 into the program's first completely successful spacewalk mission, demonstrating that underwater training could prepare astronauts for extended operations in space. The navigation backup systems that modern astronauts use when computers fail trace their origins to slide rule calculations that saved multiple Gemini missions. The star navigation techniques guiding spacecraft when digital systems malfunction evolved from manual procedures that Gemini astronauts used to determine their position and velocity. When the Gemini 6 computer failed during a critical rendezvous maneuver, astronauts Wally Schirra and Tom Stafford navigated using star sightings and slide rules while traveling at 17,500 miles per hour. The handheld radar units providing backup navigation data during rendezvous operations descended directly from equipment that Gemini crews used when their guidance computers failed. The fuel cell technology that created power crises during Gemini 5 became the foundation for every long-duration space mission since 1965. When Gordon Cooper and Pete Conrad found themselves managing a power crisis 36 hours into their mission, a faulty heater inside the oxygen tank had triggered cascading failures that threatened to end the mission on its first day. The pressure monitoring systems that detected oxygen problems during Gemini missions evolved into diagnostic systems that protect modern spacecraft from similar failures. The power distribution systems routing electricity around failed components trace their design to emergency procedures that Cooper and Conrad used to survive their electrical crisis. Commercial space companies rely on reliability standards that emerged from Gemini's explosive failures and near-fatal accidents. The multiple redundant systems protecting SpaceX crews during launch and orbital operations evolved from single-point failures that characterized early Gemini operations. The abort procedures that can save crew members from launch. Vehicle failures trace their development to ejection seats, designed to protect astronauts from exploding Titan missiles. Modern spacecraft achieve reliability rates exceeding 99%, making them safer than commercial airlines, while the Titan II's initial performance during weapons testing required significant improvement before it could be considered safe for human flight. The automated systems that make modern space missions appear routine incorporate lessons learned from every Gemini crisis and near disaster. The software preventing spacecraft from tumbling out of control evolved from Armstrong's manual recovery techniques during Gemini 8. The thermal management systems protecting astronauts from overheating during spacewalks incorporate cooling technologies developed after White's near-fatal EVA. The computer redundancy preventing navigation failures evolved from primitive guidance systems that forced Gemini astronauts to navigate using stars and slide rules when their 60-pound computers with 4,096 words of core memory failed during critical mission phases. Current Mars mission planning incorporates the same risk management philosophy that emerged from Gemini's trial-and-error approach to space exploration. Mission planners study Gemini's long-duration flights to understand how crews cope with equipment failures and psychological stress stress during extended isolation. The emergency procedures that will protect Mars-bound astronauts evolved from life-threatening situations that Gemini crews faced and survived. The training programs preparing astronauts for Mars missions use the same fundamental techniques that transformed spacewalking from a dangerous experiment into routine operations. Project Gemini's dangerous experiments and near-fatal failures created the technological foundation that enables humanity's expansion into the solar system. The program's willingness to risk astronaut lives to solve fundamental problems of space travel generated knowledge that makes modern space exploration possible. The techniques developed during 10 Gemini missions continue to guide every spacecraft that leaves Earth's atmosphere, protect every astronaut who ventures into space, and enable every mission that pushes the boundaries of human exploration beyond our home planet. Yet the men who paid this price with their blood and sweat remain largely forgotten by the public they served. The techniques these astronauts developed through trial and error became the foundation for every space mission that followed. Project Gemini's legacy centers on two principal breakthroughs: the rendezvous procedures that enable spacecraft to find and dock with each other in orbit, and the underwater training methods that transformed spacewalking from a deadly experiment into routine operations. Gemini crews like White, Armstrong, and Aldrin risked their lives testing untested procedures and unreliable equipment to solve the fundamental problems that made space travel possible. Every Dragon capsule that docks with the International Space Station uses rendezvous techniques developed during their missions. Every astronaut who walks in space benefits from the neutral buoyancy training methods that emerged from their failures. NASA's Artemis program depends on technologies that evolved from their near-fatal experiences, proving that their sacrifices created the foundation that will carry humanity to Mars.